You can tell that something is starting to move when suddenly a lot of small things happen at the same time. No big announcements, no single historic press conference, but test videos, training plans, hardware that not only exists, but is actually being used. And that's exactly the phase we're in right now. While we're recording this video, Europe, together with European Space Agency, is preparing for a rocket launch. And the United States is preparing to send people to the moon again for the first time since Apollo. As of today, Artemis 2 is scheduled to launch in February 2026, a crewed mission to orbit the moon. Real astronauts in Orion. This is the dress rehearsal for the first crewed landing next year. Artemis 2 is, in a way, a strange mission. It doesn't bring anyone to the moon, but it does something much more important. It tests whether the entire system, human, spacecraft, navigation, communication, and mission profile, works reliably outside the comfort zone of low Earth orbit. The crew has been training for months specifically for this. Long mission duration in Orion, emergency procedures, navigation without constant ground support, and re-entry at high speed. And simply keeping several people functional for days in a very compact spacecraft, a system test under real conditions. I'm Serwin, and this is Mars Chronicles. Meanwhile, everything is already building toward Artemis 3, the mission where humans are supposed to land on the moon again, currently planned for 2027. This is where SpaceX comes in. In September 2023, SpaceX released 2 videos. They show 2 engine tests. One test simulated a lunar descent burn, and another simulated a lunar descent burn of a vacuum Raptor after a longer chill and coast phase. That might sound like engineering jargon at first, but it's actually pretty central. A lunar descent burn isn't a normal braking maneuver. You have no atmosphere, no parachute, no aerodynamic stabilization. Everything that controls your descent is engines, sensors, software, and fuel management. And reigniting a Raptor after a long cool-down and drift phase is also not a given. Do cryogenic propellants behave differently in space than they do on Earth? Temperatures, phase transitions, pressure ratios, it's not just we press start and it works. So these tests aren't just for show, they're part of the answer to a very simple question. Can this system do exactly what it needs to do on the moon under mission-like conditions? To make matters more difficult, except for a few clues, we haven't seen anything of the lunar landing engines yet, which Starship needs in order not to leave a massive crater when landing on the moon. These are supposed to be positioned in the upper half of the lander. So far, however, there are only these renderings of them. In practice, it will look like this. The Raptor engines would do most of the work, and shortly before reaching the lunar surface, the dedicated moon landing engines would take over. My theory is that SpaceX has already solved this problem because they have working Draco and Super Draco engines that their Dragon capsules use. They've also created a new propulsion module for the International Space Station. They could now either use these designs or parts of them for these engines, or they've already done it. Even if the descent works perfectly, the bigger problem remains. How does the fuel even get into this ship? Starship Human Landing System relies on orbital refueling with multiple lines, long-term storage of liquid oxygen and methane in space, and minimal fuel loss over weeks. Zero boil-off is the difference between having enough reserves and having a very expensive metal object in lunar orbit or worse, on the lunar surface. Blue Origin claims they have this problem well under control now, and we have every reason to believe them. SpaceX is obviously working in the same direction, but that still has to be proven in operation, not just in presentations. And that's exactly why 2026 and 2027 won't be years of renderings, but years of test campaigns. Before the crewed landing, SpaceX and Blue Origin each have to demonstrate an uncrewed landing. Blue Origin's demo is scheduled for the first half of this year, and SpaceX plans to do theirs toward the end of the year. If you ask me, that sounds a lot like more delays, because before the landing demo, they still have to master refueling in orbit. For 2027 to hold, pretty much everything has to go according to plan. And we all know how that goes. Almost at the same time as this technical phase, the United States government released a new space directive at the end of 2025, ensuring American space superiority. The tone is remarkably sober and at the same time clear. Space travel is infrastructure, a security factor, and an economic instrument. In addition, with Jared Isaacman, National Aeronautics and Space Administration has an administrator who does not come from the traditional government apparatus, but from the commercial space industry. That doesn't change the physics, but it does change how decisions are prioritized. Less perfect programs, more flight-ready systems. When you put all that together, it paints a pretty clear picture. Artemis 2 tests whether humans can reliably operate outside Earth's orbit again. Artemis 3 depends entirely on whether human landing system refueling and long-term storage work. SpaceX is no longer testing whether Raptor works in principle, but how it behaves in this specific mission profile. And the political level makes it very clear that these programs are not affected. As a result, spaceflight has gained a much higher political significance. If you look at these Raptor tests from the fall of 2023, at first glance, you see exactly what SpaceX always shows. Fire, smoke, and a lot of noise. But the real purpose of these tests isn't in the flames. It's in what happens before and after. Because a lunar lander is a system that has to get a lot of things right at the same time, within a very narrow time window, without a second chance. You're coming from lunar orbit with several kilometers per second of relative speed. There's no atmosphere, parachute, or way to dissipate kinetic energy. All you have is thrust, control, navigation, and very little room for error. The engine has to be deeply throttleable, extremely stable in operation, and capable of the smallest control adjustments. And that's exactly the difference between a Raptor working and a Raptor working as a landing engine. An engine that's perfect on a booster can be completely unsuitable as a precision landing engine. At this point, it's worth taking a quick, practical look at what we're actually talking about here. I have here a Raptor 3 model with all the relevant geometries. This is a precision instrument. It has to be able to throttle down deeply, remain thermally stable, and respond to the smallest control commands without oscillating or becoming unstable. In the SpaceX clip of the lunar descent burn test, you can see a single Raptor with a long, stable burn. No aggressive power ramp and no wild thrust changes, which is intentional because this isn't about maximum performance, but about controllability, thermal stability, consistent thrust, and above all, predictability. A landing engine must not surprise anyone. Not the software, not the structure, and not the propellant flow. The second clip is at least just as important. It shows the ignition of a vacuum Raptor after a longer cooling phase, which simulates a drift phase. So exactly in the state in which a human landing system engine will be before descent. The problem here is not the ignition. The problem is, where is the fuel in the tank, what condition is it in, and how many gas bubbles, how much liquid, how much plasma mixture. However, these are things that are difficult or even impossible to simulate on Earth. Nothing can replace a good old practical test. In space, there is no up or down. Fuel doesn't slosh around, it spreads out, which is why ignitions after long coast phases are one of the trickiest disciplines. For your engines to work, the fuel pumps have to properly draw in the contents of the tank. For that to happen, the fuel has to be at the bottom of the tanks. Logically, and that's exactly what doesn't happen naturally in orbit but has to be forced. Liquid oxygen and methane are not friendly substances. They evaporate, change pressure conditions, cool down structures, and behave differently in a vacuum than they do on Earth. Zero boil-off is the prerequisite here for the mission to even be possible to plan. One thing that sounds like a paradox at first glance is that landing on the moon might actually be one of the easier parts of the mission. Because you can test a precise descent, you can qualify an engine, and you can simulate control algorithms. What you don't just try out is a complete refueling cycle. Over multiple flights with long-term storage and a subsequent lunar mission, followed by ascent from the lunar surface into lunar orbit. That's a chain of interdependent operations that has to work in real operation for the first time in 2026 and 27. When you put all that together, the engine tests, the fueling plans, the renderings, the architecture, it becomes pretty clear, pretty quickly. The real risk with Artemis 3 isn't the descent or even Starship itself. It's the number of things that have to work for the first time beforehand. As of now, Artemis 2 is scheduled for no earlier than February 6, 2026, a crewed lunar flyby, no landing maneuver, no human landing system, Artemis 2. I is set for 2027. That's the first real test for Starship's human landing system. Orbital refueling, long-duration stays, cryostorage, precise lunar descent, and the entire logistical chain behind it. Between these two missions, there are about 18 to 24 months in which SpaceX basically has to establish an entirely new class of spaceflight operations. That's ambitious, but it's not completely outside of what SpaceX has done before, just on a new level of complexity. With Jared Isaacman as the new National Aeronautics and Space Administration Administrator, and the clear directive to aggressively expand American leadership in space, the framework has noticeably shifted. That now means, quite specifically, that timelines are suddenly being taken seriously again, and blockers are losing influence. The new direction is pretty clear. The priorities are the moon, cislunar space, and the demonstration of capabilities. These can definitely be interpreted as geopolitical signals. China is working on its own plans for the moon, and the United States wants to be visibly there first and stay there. But what does that mean for SpaceX? SpaceX will very likely accept more risk, do more things in parallel, and fly less perfectly, but more functionally. Not because they're getting sloppy, but because they've understood that perfection is the enemy of flight rate, and flight rate is actually the real bottleneck. After all, they don't want to end up like Europe. SpaceX has some major milestones ahead this year. Launch tankers, fill depots, demonstrate transfer, show long-term storage, and repeat the whole process several times. And of course, land on the moon unmanned once, and ideally take off again. Most of that is solvable. At least SpaceX, Blue Origin, and National Aeronautics and Space Administration seem to be convinced of that. The real question is, can you stabilize this chain of operations quickly enough? Because that's exactly where it will be decided whether Artemis 3 flies in 2027 or slips more toward 2028 and 2029. From today's perspective, it looks like there will be further delays, so we can actually only expect Artemis 3 in 2028. But I'm interested in what you think. Write it in the comments. And what does that mean for Artemis itself? Artemis 2 is a classic conservative National Aeronautics and Space Administration flight, Space Launch System Orion, proven flight profiles, clear objectives. Artemis 3 is something completely different. A hybrid program, so a National Aeronautics and Space Administration architecture, plus a SpaceX system. Government safety combined with commercial speed. If that works, it will change the way exploration is done. The Raptor tests, the renderings, the human landing system hardware, and none of that is just public relations stunts. These are the first visible parts of a system designed for regular lunar missions. And that's exactly the difference. Apollo was a sprint, whereas Artemis is supposed to become an infrastructure. 2027 is possible, but not certain. The path is clear technically, though not yet proven operationally. And politically, the pressure is now so high that they won't wait for perfect conditions for years anymore. The next 2 years will decide whether the moon remains a target for individual missions or if it truly becomes a workplace. My name is Serwin, and this was Mars Chronicles. If you enjoyed this analysis, leave a subscription, write your opinion in the comments, and tell me, do you think February 6th can be met? What about Artemis 3 in 2027? Thanks to all supporters, channel members, and patrons. Thank you for tuning in. Through hardships to the stars, and respond to even the smallest rain commands.